Right now, as you watch this video, the universe is dying. Not quickly, not dramatically, but with the slow, patient inevitability of a clock winding down. Every star that burns is using fuel it can never replace. Every galaxy that drifts apart is moving toward a future where it will be completely alone. And the truly terrifying part? We know exactly how this story ends. Or rather, we know several ways it could end, and each one is more unsettling than the last. We are currently living in what scientists call the stelliferous era, the age of stars. It began roughly 13.8 billion years ago with the Big Bang, and it will continue for about another 100 trillion years. That sounds like forever, right? But in the context of cosmic time, we are living in the first few seconds of a story that will go on for so long that our entire history, every human who has ever lived, every civilization that will ever exist, is just a brief flicker at the very beginning. To put this in perspective, if the entire lifespan of the universe were compressed into a single year with the Big Bang happening on January 1st, we would still be in the first week of that year. Everything that comes after, all the darkness and decay, that takes up the remaining 51 weeks. But here's where it gets interesting. While most scientists agree on what the distant future looks like, there are several competing theories about the ultimate fate of everything. Some predict a slow, cold death. Others suggest a violent, sudden end, and a few propose something even stranger, cycles that repeat forever, or realities that simply pop out of existence without warning. Let's start with the most likely scenario, the one that keeps cosmologists up at night, not because it's dramatic, but because it's so utterly, completely final. The Big Freeze, also called heat death, is the leading theory among physicists today. The concept is simple but profound. The universe keeps expanding forever, driven by something called dark energy, a mysterious force that pushes space itself apart. As the universe expands, matter gets spread thinner and thinner. Galaxies drift away from each other, accelerating as they go, until they disappear beyond each other's cosmic horizons. Eventually, the raw materials needed to make new stars, hydrogen and helium gas, become so spread out that gravity can't pull them together anymore. The last stars begin to form, and then, after that, no more stars. Ever. Here's what happens next. For the next several trillion years, the universe slowly goes dark. The massive blue stars burn out first, living fast and dying young, then the medium stars like our sun. Finally, the last stars in the universe, small red dwarfs that burn their fuel so slowly they can live for tens of trillions of years, flicker out one by one. Imagine standing in a vast room where the lights are turning off one by one, and you can't turn them back on. Eventually, you're standing in total darkness, and you realize this darkness is permanent. That's heat death. The universe doesn't explode, it doesn't collapse, it simply runs out of energy, like a battery draining to zero. But we're still in the relatively early stages of this process. After the stars die, we enter what's called the degenerate era, lasting from about 100 trillion years to 10 to the power of 40 years from now. To understand how long that is, consider this. If every atom in the observable universe were a grain of sand and you counted 1 grain per second, you wouldn't even be close to counting to 10 to the power of 40. During this era, the only objects left are stellar corpses, white dwarfs, which are the cooling remains of stars like our sun, brown dwarfs, which are failed stars that never quite got hot enough to burn, and neutron stars, the crushed cores of massive stars, so dense that a teaspoon of their material would weigh as much as a mountain. The universe during the degenerate era is almost entirely dark and cold. Occasionally, two dead stars might collide, creating a brief flash of light, a zombie star that burns for a moment before dying again. But mostly, it's just endless night. And then something even more disturbing might happen. Protons, the particles that make up the nucleus of every atom, might begin to decay. This is still theoretical. Scientists haven't observed it yet, but many models of physics predict it will happen eventually. If protons decay, everything made of matter, planets, dead stars, even the atoms in your body if you somehow existed that far in the future, will simply dissolve into radiation and lighter particles. Matter itself becomes temporary. Of course, this slow decay assumes the universe continues expanding at its current rate. But what if it doesn't? What if gravity wins? This brings us to the Big Crunch, the opposite of the Big Bang. The idea here is simple. If there's enough matter in the universe, if dark energy isn't as strong as we think, or if it weakens over time, then gravity will eventually overcome the expansion. The universe will stop spreading apart and start pulling back together. Galaxies that are currently racing away from each other will slow down, stop, and begin falling back toward a central point. At first, this collapse would be imperceptible. Galaxies would drift slightly closer together over millions of years. But as they get nearer, gravity gets stronger and the collapse accelerates. Galaxies begin smashing into each other, their stars scattered like marbles in a bag being shaken. The space between everything shrinks. The temperature of the universe begins to rise, because when you compress gas, it heats up. The cosmic background radiation, which is right now just a few degrees above absolute zero, starts to warm. First to room temperature, then to the temperature of boiling water, then hotter. Stars that were cold and dead begin to glow again from the external heat. Eventually, everything becomes so hot that atoms break apart into their component particles. And still, the collapse continues, everything crushing down, down, down into a single point of infinite density, a singularity, the same kind of singularity that our universe was born from. This raises a fascinating question. If the universe can crunch down to a singularity, could it bounce back out again? The Big Bounce theory suggests exactly that. Instead of ending in a final singularity, the universe compresses until it reaches some minimum size, and then the laws of quantum physics kick in and force it to expand again. Another Big Bang, another 100 trillion year cycle of star formation, another slow death, or another crunch. This implies we might be living in an infinite cycle, and this universe, the one you're living in right now, might be the billionth or trillionth iteration. Everything that's ever happened might have happened before in previous universes, and it will all happen again in future ones. But let's return to our timeline, because while the Big Crunch and Big Bounce are possibilities, most evidence suggests we're headed for heat death. After the degenerate era, after even protons have decayed, we enter the black hole era. This lasts from 10 to the power of 40 years to 10 to the power of 100 years. At this point, the universe is essentially empty except for black holes, the last major structures left. These black holes are the graves of dead galaxies, containing the crushed remains of trillions of stars. And they just sit there in the void, warping space and time around them. But black holes aren't immortal. Stephen Hawking discovers that they slowly leak energy through a process called Hawking radiation. A black hole loses mass so slowly that a black hole the mass of our sun would take 10 to the power of 67 years to evaporate. The supermassive black holes at the centers of galaxies, the ones that weigh billions of times more than the sun, take even longer. But eventually, over timescales that make the age of our current universe look like a single heartbeat, even these giants shrink and shrink until finally they explode in a final burst of radiation, releasing the last bits of organized energy back into the void. And then we enter the dark era, 10 to the power of 100 years and beyond. This is the true end state of the universe under heat death theory. Nothing remains except photons, particles of light that have been stretched by the expansion of space until they have almost no energy left. No stars, no planets, no black holes, no atoms. Just an infinite dark ocean of nearly motionless particles spreading further apart forever. Entropy, the measure of disorder in the universe, has reached its maximum. No energy can flow from one place to another because everything is at the same temperature, just a fraction above absolute zero. Time, in any meaningful sense, stops because time is change, and nothing changes anymore. The universe has become a graveyard, and it will stay that way forever. Unless, of course, something else happens first, because while heat death might be the most likely end, there are other possibilities that are far more sudden and far more terrifying. The most disturbing of these is called false vacuum decay, and it could happen right now. The idea is based on quantum field theory. The universe is filled with fields, like the electromagnetic field and the Higgs field. These fields exist at certain energy levels, and we assume they're at their lowest possible energy state, their true vacuum. But what if they're not? What if the fields that give particles their properties and hold atoms together are actually in a false vacuum, a temporary state that seems stable but isn't the lowest energy configuration? If that's true, then at any moment, a random quantum fluctuation could trigger a transition to the true vacuum. When this happens, a bubble forms. Inside this bubble, the laws of physics are different. The forces that hold atoms together might not exist. Chemistry doesn't work. Matter as we know it can't exist. And this bubble expands outward at the speed of light, consuming everything in its path. Because it travels at light speed, you would never see it coming. Light from the bubble can't reach you before the bubble itself does. One instant you exist, the next instant you don't. Not dead, not destroyed, simply edited out of reality. And this bubble could appear anywhere in the universe at any time. It could have already formed on the other side of the observable universe and be racing toward us right now, and we would have no way to know until the instant it arrives. A similar but slightly different scenario is the Big Slurp, which is related to the Higgs field specifically. The Higgs field is what gives particles mass. If this field becomes unstable and drops to a lower energy state, it doesn't just change the laws of physics, it could cause space itself to collapse inward, compressing the entire universe into a small, dense ball. The effect is similar to vacuum decay, sudden, unstoppable, and total. Then there's the Big Rip, which is the violent cousin of heat death. This theory assumes that dark energy, the force pushing the universe apart, doesn't stay constant but gets stronger over time. Right now, dark energy can push galaxies apart, but it can't overcome gravity on smaller scales. That's why our solar system stays together, why you're not being pulled apart right now. But if dark energy increases, it will eventually become strong enough to overcome gravity on every scale. First, galaxy clusters are torn apart. Then individual galaxies shred as stars are ripped away from each other. Then solar systems, the Earth torn from its orbit around the sun. Then planets themselves explode as the dark energy overcomes the electromagnetic forces holding molecules together. In the final fraction of a second, atoms are ripped apart. Every particle in the universe is isolated, separated from every other particle by the violently expanding space between them. This doesn't happen slowly over trillions of years. Depending on how fast dark energy strengthens, the Big Rip could occur in as little as 20 billion years, not much longer than the current age of the universe. Now, if all of this has left you feeling small and insignificant, there's one more mind-bending idea to consider. In the dark era, when the universe is essentially empty, quantum mechanics suggests that random fluctuations could still occur. With enough time, and we're talking timescales of 10 to the power of 10 to the power of 50 years, or longer, these fluctuations could randomly arrange particles into complex structures, including, theoretically, a human brain. This is called a Boltzmann brain. It would pop into existence with completely false memories of a life that never happened, exist for a fraction of a second, and then dissolve back into the void. And here's the disturbing part. Given infinite time, it's statistically more likely that you are a Boltzmann brain hallucinating your entire life right now than a real person who evolved on a real planet. Of course, this is more of a philosophical puzzle than a scientific prediction, but it showed us just how strange the far future could be. So, where does this leave us? We're living in the bright, energetic youth of the universe, a brief window where stars shine and life is possible. The stelliferous era won't last forever. In cosmological terms, it barely lasts at all. What comes after is either a slow fade to nothing, a violent rip into oblivion, a crushing collapse back to a singularity, or an instant deletion by a bubble of altered physics. No matter which end awaits us, the conclusion is the same. Nothing lasts. Not stars, not galaxies, not even atoms. The universe is not eternal, and neither is anything in it. But there's something oddly comforting in that. Knowing that everything ends, that even the stars have a lifespan, makes the time we have feel more precious. We exist in a universe that is slowly winding down. But for now, in this moment, we're here to witness it, and that's something worth appreciating while the lights are still on.